Our presentation is on the analysis and redesign of a food processor by Anubhav, Liberty, John, and Shungo. A food processor is designed to expedite and improve the chopping of food, and we estimate a production of 120,000 units per year. We selected this product as there is ample opportunity for improvement. Our primary customers are adults using the device in their homes. Our secondary customers are restaurants and commercial kitchens. We performed functional analysis and determined that the main function of the food processor, to chop food, was possible if the device could contain food by preventing leakage and allowing filling, blend food by mixing and reducing food, assure dependability by acting uniformly and preventing injury by securing components and reducing speed, assure convenience, enhance product by reducing chopping time, and please sensors with features to vary speed and facilitate cleaning. Two feasible assembly sequences were identified as the most logical and simplest to follow. Sequence A starts with the base of the product before adding on the housing and ball components, enabling the most Z assembly. Sequence B starts with the housing and ball components before adding on the base of the product, with sub-assemblies more useful to test the function. Sequence A scores higher than B as it aimed to mitigate the number of rotations required and maximize tool access.
This is a function component mapping matrix for a food processor. The functions were found from functional analysis done earlier, and the listed components were found from the leaves of the fishbone assembly diagram. As you can see, there's some components that are able to perform many basic functions, but for some functions only one component or two components are able to do it. This can be a cause for inefficiency. This is the bill of materials for our food processor. We had to make a few assumptions in order to help us calculate costs. The first assumption we made was assumed production of 100,000 units. The second assumption we made was that tools and machineries had a useful life equal to the total units being produced. We approximated labor rate to $15 per hour. The total cost came to be $62.94, which is about 40% of retail price of an average food processor. Standard parts such as springs and screws and other fasteners were bought at retail price and had no process or tooling costs. The motor was also assumed to be bought at retail price.
So what we want to do when we talk about redesigning it for manufacturing and assembly, we mostly just want to get rid of a lot of parts. There's a lot of really unnecessary parts. There's these 4 rubber feet in the bottom, really don't need to be there, they can go. The main and upper housing, they're separate parts right now, but they really don't have a reason to be. There's no fasteners, they should just be merged into one part. There's 2 compound gears, those should just be a single part. Why not? It's injection molded plastic. And then there's a separation plate, which really could just be part of the main housing. Like it doesn't have a reason to be a separate individual part. To accommodate this, we need to move a couple parts around so that everything can be assembled easily. The motor and input gear needs to be moved, but that's a relatively simple task. That might result in potential gear ratio changes, or if we don't change the actual gear ratio, then what we can just do instead is keep the gear ratio the same, but just change the size of the gears. When we talk about redesigning everything for different product families, one of the things that we wanted to do was we want to keep the primary and secondary customers having mostly the same components. The housing, the bowl, the gear train, these should be the same between the two. For the secondary customers, we want to, as industry users, we want to give them a stronger motor, get better cooling in the base, but those are 2 parts, very easy change. And then for the primary consumer, we want to have different attachments which they can swap out, things like different lids that they can drop food into, or bigger blades, or larger lids so they can accommodate more food.
This slide shows the product family assembly sequence, and we see that from the very first, the lid, the primary customer product showing blue and the secondary customer product part showing yellow are already branching out, which means that even though not all the components have multiple variants, they have to follow a different assembly sequence due to the fact that this product family is already branched out from the lid to the blade and all the way to the separator plate, resulting in having so many nodes compared to the next slide that you'll see in a second. This slide shows the improved product family assembly sequence, and the first 7 green nodes shows the steps that involve only part with only one variant before branching out to assembling parts with more than one variant, such as a blade. And this allows to have less number of assembly steps and consolidate the assembly sequence depending on each customer group that we target to make the product for.